some girls are very stupid. How would she move around with this? You fine?
Hello, mom.
This is mom and dad.
We're learning. We're learning, mom.
Okay, Mike.
We are learning.
Okay, Mania, it's streaming.
Yes, ma'am.
So someone should please check for the audio.
You are online, right? You're not live.
Hey, Chibo came. Wow.
Oh no, like, this is not laptop, please. I can make it now. Okay, it's easier on phone. Okay.
This one here. High taskbar. Okay, so I presume you all can hear me, and sorry about the whole delay. We had to make sure that everything is okay before we started class. Okay, so we'll start. As we all know, we are dealing with gas laws today, and then we would get to solve every question or as many questions as possible on gas laws. The basic rules for the class is, please, the comment section for now, just stop commenting. As many of you as are here should please stop commenting. Okay, so we could start the class and have a little sense of decorum. Now, okay, so having said that, we would get into the study. I would Okay, now we'll get into the class for want of time so that we'll get to finish it early. The very first thing we are going to be discussing is like an introduction to the class, and that is the concept of gas laws. First of all, we need to understand what a gas is. Now, a gas is simply described as a state of matter in which constituent particles are in constant random motion. So what do I mean by that? The simple implication of that statement is that once you have a particular substance and that particular substance is in compact and they are not necessarily constantly moving, because of that we cannot refer to this thing as a gas. But gaseous particles are always moving, like imagine smoke, for instance, or water vapor. The particles are constantly moving and their motion is not organized. That is the first thing you need to note. Now, to be able to understand gas laws, which is the main thing for this study, there are specific properties that must be discussed, and I will be introducing them. The first thing we need to understand is pressure. Okay. Sorry about the whole technicalities and the delays anyway, but let's continue the class. Now, as I was saying, when you say pressure, the pressure of a gas simply describes the force per unit area of a particular substance. When you're looking at the effect of a force on a unit area, that is when you are describing the pressure. So have that in mind, that pressure is force per unit area. However, the emphasis with respect to gas laws is this: pressure of gases in a container is exerted as a result of collision between, for instance, a container like this, and you have gases inside. When you are considering the pressure of this particular gas, you are looking at the effect of the force of this particular gas colliding against these walls. So have that in mind. The pressure of gases in a container is exerted as a result of collision between the gaseous particles and the walls of the container. A very important point, and we can actually look up a question on that. Let's see, one of the jam pass questions. Let's see if we have that here. Okay, so if we consider this question now on the screen, the question says an increase in temperature causes an increase in pressure of gases because the increase in the number of collision, that's option A, it increases the number of collision between gaseous molecules. Option B, the molecules of gases bombard the walls of the container more frequently. Option C, it increases the number of collision between the molecules of the container more frequently. So have that. Now, having mentioned this, as I said, we would now get to discuss some important things about pressure though, and those important things are basically the major units of pressure that you have to take note of. The major units of pressure that you have to take note of. Okay, now the first one is ATM. That's a very popular one. The first one is ATM. So units of pressure, you have ATM. Units of pressure are ATM. Okay, let me take this out. Let's take measuring pressure in atmosphere. That is the unit. The second unit of pressure that you are going to deal with is the popular one, millimeter mercury. Yes, millimeter mercury. Another unit of pressure is bar. Another unit of pressure is bar. You also have as torr. You have Newton per meter squared. You have Pascal, and so on and so forth. So it's important that once you see any of these units in a question, if I say 2 ATM, automatically you know that you are dealing with a pressure. If I say 5 millimeter mercury, you just know that that particular value is a. That we need to take note of something, and what is that? Every time a particular process is carried out in chemistry, in ATM, standard pressure in ATM, standard pressure in ATM is 1 ATM. And this 1 ATM is equivalent to 760 millimeter mercury. What does this mean? Anytime they say at STP, it means that the value of the standard pressure would be 1 ATM, 760 with other units. I mentioned ATM, millimeter mercury. If it is centimeter mercury, it will be 76 centimeter mercury. Another value for standard pressure is 1.01325 times 10 raised to power 5 Newton per meter squared, which is also the same thing as 1.01325 times 10 raised to power 5 Pascal. All these things I'm writing now are the units of standard pressure, but in different versions, basically. So these are the values of standard pressure in different units. So if you are measuring in ATM, your standard pressure will be 1 ATM. If you are measuring in millimeter mercury, your standard pressure will be millimeter mercury. If it is in centimeter mercury, your standard pressure would be 76 centimeter mercury. And once you are dealing with Newton per meter squared, your standard pressure would be 1.01325 times 10 raised to power 5 Newton per meter squared, basically. Now, having mentioned this, there are others, and the other ones could include torr, and torr is 760 torr. You could also have pressure measured in bar, and when pressure is measured in bar, it's 10 raised to power 5 bar, basically. So you have that these are the units of standard pressure. Now, Having mentioned this, I would like to go to the next concept, or the next important property or feature that is needed, and that is temperature. Now, basically, temperature simply describes okay. So sorry about the delay. We noticed some technical issues and we are working on resolving them. So, but once you notice you can't hear or you can't see, please just notify us in the comment section. Okay. Now, continuing the class. I said that the next property that we're going to be considering under gases is the property of temperature. Temperature. Now, basically, as we all know, when you say temperature, temperature is simply the measure of the degree of hotness or coldness of a body. It is also the measure of thermal energy in a body. We don't necessarily need to write down this definition. The important thing to note about temperature is that when you are measuring gases, whenever you are calculating with respect to gases, you use the temperature unit of Kelvin. You use the temperature unit of Kelvin. So when you're giving your temperature in degrees Celsius, it's important to note that you should convert degree Celsius values to Kelvin. Now, it's very simple to do the conversion. How do we do it? Kelvin is equals degrees Celsius plus 273. What does it mean? If you are given a value in degrees Celsius, you are expected to convert it to Kelvin. How? You simply add 273 to the degree Celsius. Or yeah, example, imagine they say convert 25 degrees Celsius to Kelvin. What I simply do is my Kelvin value will now be this place that is we have degrees Celsius. I'll put the value, and what's the degree Celsius value? 25 degrees Celsius, and I'll add 273. Now, on addition of these things, what we're going to get is 298 Kelvin. Quite simple. Please note, I'm saying it again, that once you have a value in degrees Celsius and you are dealing with a gas law, or you are dealing with a calculation in which temperature is related to the gas, automatically the first thing you are supposed to do is to convert your degrees Celsius to Kelvin, basically. Now, just as we mentioned, you can actually do the other way around, that is converting Kelvin to degrees Celsius, and that's going to be degrees Celsius equals Kelvin minus 273. So if, for instance, I tell you that I want to convert something like 273 Kelvin to degrees Celsius, it's simply going to be 273 Kelvin minus 273, and what I'm going to get is 0 degree Celsius. So have that in mind. Okay, sorry, but I presume you know that what is here is 0 degrees Celsius. Okay, so as I was saying, that when you are dealing with temperature of gases are not measured in degrees Celsius. Once you have a degree Celsius value, make sure you convert it to Kelvin. And how do you do that? Just add 273, basically, and that's that. Now, and when we said standard pressure, we gave the values for standard pressure. Temperature also has standard values. The standard temperature is basically equals 273 Kelvin. So when you say standard temperature, what you have as standard temperature is 273 Kelvin. If I want to convert it to degrees Celsius, I'm going to use degrees Celsius equals Kelvin minus 273, which is going to be 273 minus 273 equals 0 degrees Celsius. So which means that when I say standard temperature, the value I'm going to put in whenever I say standard temperature is 273 Kelvin. You know I can't use 0 degrees simply because when you're measuring or calculating for gases, you use Kelvin values. So that's that basically. Now, with that said, these are the major or most important things to take note of. There are other factors or other things that can be involved in dealing with gases, like the amount in mole and the volume. As we all know, volume is simply the space occupied by a substance. When you're considering the space occupied by a substance, that is simply the volume. Now, things to note about volume. The unit of volume, there are major units of volume, and those units that we are going to be coming across, especially for those of you that are writing JAM, is cm cube and dm cube. In some cases they might include liter, but just take note of these things about volume. First of all, about volume is that 1 dm cube is equals 1 liter. That's the first thing. That if you see liter in a question or you see dm cube, they're exactly the same thing. So when I say 20 liters, it's the same thing as saying 20 dm cube. Now, the next thing to take note of is that 1000 cm cube is equals 1 dm cube. 1000 cm cube is equals 1 dm cube, which means that if I have, for instance, if I want to now do a conversion, it's going to be simple for me to do the conversion. The conversion will now be V in cm cube would be equals V in dm cube times 1000. When I now want to convert dm cube to cm cube, it's going to be V in dm cube is equals V in cm cube all over 1000. So please, these things I'm doing as preambles before I get to discuss the main study are things that I will not be repeating when the class starts fully. So just have that in when I get into gas laws, I meant to say. So these preambles are things that you should take note of. I said that the volume in dm cube is equals the volume in cm cube over 1000, because most of the questions you're going to be coming across in the UTME exam would be questions that are relating cm cube to dm cube. Okay, now having said this, it means that anytime I see dm cube, cm cube or liter, and maybe I did not mention that that is a volume, once you see dm cube and liter, just have that in mind that that is a volume. And with that said, we can now get into the gas laws. Now, there are about 9 major gas laws we're going to be considering. As I said, what we're going to do is we'll take the law, take references, and take a question, and that will be that for the law. So please pay attention. Now, I would allow questions once I'm done solving a particular question. That's, I give you a question and finish solving it. Once I'm done solving that particular question, I can take questions in the comment section. So just put out when you have a question, take note of it, and when I call for the question, just put it out so that we'll take 1 or 2 questions before we go to the next law. Okay, now having said that, the 9 gas laws include, the first one is Boyle's law. Oh no, that's the wrong spelling of Boyle's. Okay, Boyle's law. Oh, that's supposed to be a Y. My handwriting is terrible. Manage. That's supposed to be, yes. Just know that that's supposed to be a Y. So Boyle's law. Then after Boyle's law, we have Charles' law. Charles' law. We have Amunton's law. And then the next one is the general. This is supposed to be a G. General gas equation. And after we are done with that, we'll get into the ideal gas law. And after the ideal gas law, we will now get to discuss Avogadro's. I think we are going to discuss Avogadro's first. Let's take that order, because Avogadro's, if you need to understand Avogadro's to be able to understand the ideal gas law. So we'll take Avogadro's, sorry about that, law first. Then after that, we'll take the ideal gas equation, and after we are done with the ideal gas equation, we will now discuss Dalton's law of partial pressure. You can actually write it in full if you want to. Yeah, finish up Dalton's law of partial pressure. And once we are done with Dalton's law of partial pressure, we'll get to discuss Gay-Lussac's law. This is supposed to be a C. Gay-Lussac's law of combining volume. And then finally we'll discuss Graham's law. So I think this is like, there are 9 laws: 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. So there are 9 laws, and we're going to be discussing them. Now, as I said, we're going to start with the first one, take things about it, take down the major formula required. And once you're done with that, we'll answer one question. Now, moving ahead. So what is Boyle's law? Boyle's law simply states that the volume of a given mass of gas, is inversely proportional to pressure at constant temperature. So it is expressed mathematically like this. I take it again. The volume of a given mass of gas is inversely proportional to pressure at constant temperature, basically. So once you have volume, it's inversely proportional to pressure. Now, the term inverse proportionality simply means that once a particular quantity is increasing, the other one will be decreasing. So have that in mind. When I say inverse, it means that if the volume is increasing, automatically your pressure should be decreasing. Now, it can actually help you in questions. How do I mean? When you look at your options, maybe you have a question where there is an increase in pressure, it means that the new volume has to be decreased, because as the pressure is increasing, the volume should be decreasing. Have that in mind. Inverse proportionality implies that when this is increasing, the other one is decreasing, and vice versa. Now, the second thing to note before we continue is when you have a question and you notice that in the question they said constant temperature. Another way to say constant temperature is that the temperature remained the same or the temperature did not change. Once you see those kind of questions, just know that it is Boyle's law, basically. Now let's look into the mathematical expression. The mathematical expression of Boyle's law is derived from this. And what do we have? If we introduce a constant k here, the formula will now be k is equals Vp, which means we'll have V1 P1 equals V2 P2. This is the formula for Boyle's law. Now, when do we use this formula? If temperature is constant. So once you notice that temperature is constant, please do not mind my handwriting, but just try to learn with what we're doing. Now, once you notice that temperature is constant, automatically you are supposed to use V1 P1 equals V2 P2. Let's look at a question to help us understand what I'm saying. The question we're going to consider, let me put that up in the screen for everybody to see. Yes, okay. So Boyle's law 1. Okay, so let's put it up for everybody to see. I presume you can see it now. So if you look at the board, the question on the board says the pressure on 100 cm³ of oxygen at 35 degrees Celsius is 750 millimeter mercury. So I would even like to be taking note of these things so that you know, basically when I solve questions, what I do is I take note of the parameters. So taking note of the parameters, we have that they said the pressure of 100 cm³. The first volume we are seeing there is 100 cm³, which means our V1 is 100 cm³. Now, having mentioned that, they now said the pressure of 100 cm³ of oxygen gas at 35 degrees Celsius is 750 millimeter mercury, which means the pressure associated with that 100, which is P1, is 750 millimeter mercury. So you keep writing those things out. You can do that as I'm doing it. They now said, what would be the volume of the gas if the pressure is increased to 1000 millimeter mercury? Now, they are asking you to find a new volume, which is V2. We don't have that. If the pressure was increased from 750 to 1000, which means the new pressure is going to be 1000 millimeter mercury. Okay, now with that said, we have gotten the parameters. That is not everything to the question. Now let's take the question together after writing this thing. They said the pressure on 100 cm³ of oxygen at 35 degrees Celsius is 750 millimeter mercury. What would be the volume of the gas if the pressure is increased to 1000 millimeter mercury without changing the temperature? So the emphasis in this particular question is the term without changing the temperature, which means temperature is constant. And as we know, once temperature is constant and you are relating volume and pressure, what we are dealing with is Boyle's law. So using Boyle's law formula, everybody can attempt and then put out their answers. Let's see. So solving the question, Boyle's law formula is V1 P1 equals V2 P2. Now our initial volume was 100 cm cube multiplied by the pressure, which is 750. Sorry, sorry about this. Okay, so I said solve it on your own if you want to, but I'll solve that too. So 100 cm cube multiplied by the initial pressure that we wrote earlier on is 750, and as you can see is equals to the new volume multiplied by 1000. So which means the new volume will now be 100 cm cube multiplied by 750 divided by 1000. 0 cancels 0, 0 cancels 0, 0 cancels 0, and 1 times 75 is 75 divided by 1. So which means the new volume is going to be 75 cm cube. Now I hope we know why it is 75 cm cube, because you are looking for volume, and besides that, this is supposed to be millimeter mercury and this is supposed to be millimeter mercury, which cancels out. So which means what is remaining is just cm cube. So have that in mind, that the new volume is 75 cm cube. Now notice something in the question. We notice that immediately the pressure went from 750 to 1000. We are noticing an increase. Pressure increased, and as pressure increased, you notice that your volume decreased. So you find out that our answer, as we found out, is going to be option C, which is the volume equals 75. I presume that's what we all got too. Okay, having said that, is there any question based on what we solved? If you have questions, this is the time to put it out. There's a little delay with YouTube though, so it might take you a while. So I'll be waiting like 1 minute to hear from you with respect to the questions. Okay. Boy, in class.
What? Then smack you, use your brain.
Okay, so for now I've not seen any question. There's a lag, so that's why I need to wait till I see a question. If there is no question, we would have to continue. Okay, so I'll come back to it anyway. Now maybe we'll try one more question. You guys should try this other question, so we'll see. Okay, try this question. Everybody should try this question and post the answer in the group. Like 30 seconds. Attempt this question. 30 seconds to 1 minute. Everybody solve. Let's have our answer so that we'll move ahead. It's a very simple question. So I don't understand the first one you did, please. So, you that what you said pressure is decreased. Wow. I did that, guys. Putting this up. And the service is I presume we have our answers now, so you can put them out. I guess they are all out by now. Basically, sorry, we're just trying to make the class very smooth. Okay, so we have answers coming in 2v cm cube. Those in the physical class, what do you people have? 2v cm cube. Okay, now let's solve it together. Now, to solve this question is going to be quite simple. So let's look up. The question says that the volume of a given gas is VCm cube. The volume of a given gas is VCm cube. I presume the audio is still here. Just confirm. Those online, confirm. Hope you are. Okay, good. Now, as I was saying, the volume of a given gas is VCm cube. Now, please, let's put that down, that the first volume that we are seeing is VCm cube. Most of the times, you might not be giving values, but just write out whatever is given. They now said, I think that should be at a pressure of P millimeter mercury, which means the first pressure associated with this volume is P millimeter mercury. Oh, sorry, something happened. Let me restart that again. The volume of a given mass of gas, according to us, the first volume we are seeing is VCm cube. And then we have that the second volume, the first volume is VCm cube. The first pressure is P millimeter mercury. Now they now said, what is the new volume? Which means we are looking for the V2. The new volume, question mark, of the gas if the pressure is reduced to half. So it means that P2 would now be the initial pressure, which is P millimeter mercury, divided by 2. Hence, our P2 is going to be P over 2. Okay, now with that said, they said at constant temperature. Once you hear at constant temperature, for those of you that have been asking the question, why did we use this formula? If you see at constant temperature, just know you are dealing with Boyle's law. And what is Boyle's law formula? I'm taking this out. Boyle's law formula is equals V1 P1 equals V2 P2. Now, what does this simply mean? We are going to input our values. The initial volume of this particular question is VCm cube. The initial pressure is P millimeter mercury, and that is equals the V2, which we don't know, multiplied by our pressure. The pressure 2 is half of pressure 1, which is P millimeter mercury divided by 2. With that said, you make volume 2 the subject of formula because that is what you are looking for. They said the new volume. So V2 is going to be equals VCm cube times P millimeter mercury divided by P millimeter mercury all over 2. Now, as we know that once you have a fraction, that's a number divided by a fraction, you simply take the divisor of that particular fraction up and multiply it, and then that is going to be V2 equals VCm cube times P millimeter mercury times 2, all divided by P millimeter mercury. Okay, yes, you cannot see that part. Anyways, the point is P millimeter mercury cancels out, and once it cancels out, what you are going to have, see our answer, let's come up. Our answer, V2, oh my god. So V2 would now be equals VCm cube times 2, and that is going to be 2 VCm cube. Now please, the first thing which I said initially, or the things I said you should emphasize about Boyle's law, number 1, you are relating volume and pressure. Secondly, the pressure and volume, after they are related, you must see in the question that the temperature is constant. So once you see a question where volume and pressure is related and they say constant temperature, class, just know what you are supposed to do is V1 P1 equals V2 P2. There's not that thing, just that's how it is. So have that in mind. Anyways, we'll try more questions at the end of the class, but we need to go to other laws to see how things are. If you are not following, just put out your complaints. The technical team is actually going through them, and once we notice your complaint, we'll respond to it. Okay, thank you very much. Now we'll have to go to the next law for want of time. I presume this was understood to a very great extent. Now the second law we are going to talk about is Charles' law, and Charles' law is quite simple. Charles' law simply states that the volume of a given mass of gas is directly proportional to absolute temperature, provided that pressure remains constant. I take it again. Charles' law states that the volume of a given mass of gas is directly proportional to absolute temperature, provided that pressure remains constant. Now, why did I have to bring this up? It simply is expressed mathematically as this: V is directly proportional to T. In my definition, or when I was stating the law, I said absolute temperature. Why did I make mention of absolute temperature? It means that if your temperature is in degrees Celsius, for you to relate it to volume, you must convert it to temperature in Kelvin. And few facts about temperature in Kelvin. The first fact about temperature in Kelvin is that the lowest possible temperature in which gases exist is referred to as absolute zero. I take it again. The lowest possible temperature in which gases exist is referred to as what? Absolute zero. Absolute zero is 0 Kelvin. Now, when I say 0 Kelvin, 0 Kelvin, converting it to degrees Celsius, everybody should try it out. If you convert it to degrees Celsius, I told you that degrees Celsius is Kelvin minus 273. Why Kelvin is equals degrees Celsius plus 273. So I want to convert this 0 Kelvin to degrees Celsius, and what is it going to be? 0 minus 273, and eventually it's going to give us minus 273 degrees Celsius. So just have that in mind, that when you are dealing with the lowest possible temperature, it's not 0 degrees Celsius, it is 0 Kelvin, and 0 Kelvin is the same thing as minus 273 degrees Celsius. Now, with that said, let's try out this question before I continue the Charles' law explanation, because I saw a question on JAM that has to do with this absolute zero. Let's see the question. Where is it? Okay, that's the question. Okay, so the question says, according to Charles' law, the volume of a gas becomes zero at dash. So let's look at the options. You can send your comments so that we'll review them and then I'll answer the question. So what do you think? Based on what we said, what do you think is the answer? Okay, so due to the lag, the answer is minus 273 degrees Celsius. Why is it minus 273 degrees Celsius? Once you hear that the volume of a gas becomes zero, it simply means that you are looking at the lowest temperature. The temperature at which gases cease to exist, as we mentioned earlier on, is absolute zero, and that's the lowest possible temperature. That lowest possible temperature is 0 Kelvin. And when I say 0 Kelvin, as we said in the question, they did not give us our values in Kelvin. What they gave it to us is in degrees Celsius. That's why I had to talk about that. So when you have 0 Kelvin as lowest temperature, and lowest temperature is the temperature where the volume of a gas is zero, which is 0 Kelvin, how do you convert it to degrees Celsius? Very simple. Degrees Celsius is equals Kelvin minus 273, and once you have that, degrees Celsius will be the Kelvin value for which the volume of gas is 0 Kelvin. And once you minus 273, you are going to have that the degrees Celsius value will now be minus 273 degrees Celsius. And if you look at that, that is option C, and that's why that's your answer. So basically, with that, we can move ahead. Now, back to what I said. The mathematical, let me take this question out. Sorry for the delay. Just trying to make sure that everybody. Okay, so having said that, when you say Charles' law, as we said, Charles' law simply states that just please screen back. Okay, so as I was saying, Charles' law simply states that the volume of a given mass of gas is directly proportional to absolute temperature. Please, I did not say absolute zero. I said absolute temperature. When I say absolute temperature, it means that you are measuring in Kelvin. So I take it again. The volume of a given mass of gas is directly proportional to absolute temperature, provided that pressure remains constant. And what does that mean? It simply means that my expression, sorry, there's a little technical issue, so let's resolve it. Okay, sorry for the, we are trying to resolve a lot of things so that the class will be very effective. So as I was saying, the volume of a given mass of gas, that's Charles' law, is directly proportional to absolute temperature. Remember, once you say absolute temperature, it means that it's measured in Kelvin. That's why I said open your value in degrees Celsius. Sorry, Igbo. And Mona Lena, if your value is in degrees Celsius, it is supposed to be converted to Kelvin, and I've shown you how. Kelvin is equals degrees Celsius plus 273. Now, moving ahead, remember that I ended the law by saying at constant pressure. What does this mean? Once you have a question that is relating volume of a gas and temperature, and they say at constant pressure, just know that the formula you are going to use is that of Boyce-Charles law, and Charles law's own is V1 over T1 is equals V2 over T2. I'm not going to bother deriving that. If you know your variation, you should know that this is for Charles law. And where did I say you use it? At constant pressure. So once your pressure is constant, that is exactly where and when you use the Charles law, basically. Now, with that said, we are going to try a question. Let's look at the question so we understand how this works. Okay, so the question we are going to be considering is okay, sorry about the little delay. Let's continue. Now, the question we can see on the screen says that a given mass of gas occupies 2 dm3. So let's put down that the first thing we are seeing is that the first volume in this question is 2 dm3. A given mass of gas occupies a volume of 2 dm3 at a temperature of 300 Kelvin. So the initial temperature for this volume is 300 Kelvin. Now, we don't need to do any conversion here simply because it's already in Kelvin, so we can solve with this. If it was in degrees Celsius, when I know what to do now, we'll convert the degrees Celsius to Kelvin, but it is already in Kelvin, so we don't need to convert it. Then they said, at what temperature? Which means we are looking for a new temperature. So T2 is what we are looking for. At what temperature will the volume, that is the new volume, be doubled? So the new volume would now be double is 2 of the initial volume. And what is that initial volume we have here? 2. So that's 2 times 2 at constant pressure. That is keeping pressure constant. Now please, once you see that pressure is constant, we've already said this, that if pressure is constant, what we are dealing with is Charles law. Now remember, this is 2 dm3, and hence our new volume is going to be V2 equals 4 dm3. Now, as we said, I hope we understood how we got this 4 dm3. The question says, what will be its new volume? What will be the temperature if the volume is doubled? And when you say double volume, it means 2 times whatever initial volume you had. That's why we did 2 times 2, and we got 4. With that said, we'll get to solve this thing using the formula. What formula are we using? We're going to use the Charles law formula, and that is V1 over T1 is equals V2 over T2. The initial volume in this question is 2 dm3. The initial temperature, which is already in Kelvin, is 300 Kelvin, equals the final volume is 4 dm3, and the final temperature is what we are looking for. So class, everybody cross multiply and find out the answer. The answer is going to be T2 is equals 4 times 300 is 1200 divided by 2 1 2 divided by 2, and we're going to have 6, sorry about that, 600 Kelvin as our final answer. And what option has 600? Option D. So you find out that is okay. So if you have issues, send your questions out to the comment section and we would respond to them. Now, having said this, you guys should try out this particular question. Those online, those viewing the class, just try out this question. Sorry, let's get the question on the screen. Okay, your question is up. So everybody should try out this question. So let's try this question and get the answer. You have exactly 1 minute to solve it. 1 minute to solve it. Okay, do I have answers? Okay. Well, as I said, if you look at the question, fixed pressure simply implies that you are using Charles' law. So please be fast about it and put out your answers. You said I should tell them. If you can't see the board, please, some of them are supposed to get small technical knowledge. Increase the resolution from 360 to 480. You will see it clearly. You get, change your resolution from 360 to 480 and the board becomes clearer. Okay, I presume somebody has an answer. What answer do we have here? Those in the live class, in the physical class. Yes? Anybody? Nobody has gotten an answer. Okay, let's solve this question. So, to solve the question, sorry about that. As I said, okay. So, do we have an answer? What did you get? Nobody has solved this question. Oh yeah, let's look up. So let's look up and solve the question. Now, the question says, if 30 cm cube, please, that is the first volume. If 30 cm cube, how do you know that that is a volume? Look, as you can see, you will notice that this is cm cube, dm cube, liter. Everything that has to do with cm cube, dm cube, or liter is a volume. So that's why here our first volume is going to be, oh sorry, our first volume, okay, our first volume is going to be 30 cm cube. Now they said if 30 cm cube of a gas at 50 degrees Celsius is warmed, so the first temperature for that particular volume is 50 degrees Celsius. But you know what I said about degrees Celsius? Do not solve with degrees Celsius, convert it to Kelvin. How? 50 degrees Celsius plus 273. That means our first temperature will be 50 plus 273, and that's going to be 323 Kelvin. Yes, that's what it's supposed to be, 323 Kelvin. Then we go to the next one. Then I said is warmed to 80 degrees, which means the new temperature is 80 degrees Celsius. Now, that 80 degrees shall not be used, cannot be used, and will never be used. Why? It is in degrees Celsius. So what do you do to 80 degrees? You add 273. Adding 273 to 80 degrees would now have 353 Kelvin as our new temperature. That is the second temperature. So I noticed that some of your mistakes might have been that you started solving with degrees Celsius. So please note, if you are given a value in degrees Celsius, add 273 and convert it to Kelvin. For the new temperature, we had 353. So let's continue. Now, they said at a fixed pressure. That statement, at a fixed pressure simply implies that you are going to be dealing with Charles' law, which means you are going to be dealing with V1 all over T1. Sorry about that. So that is V1 over T1 equals V2 all over T2. Now, if we look at the question says the fractional increase in the volume is dash. This is actually something we can find out and resolve with this particular formula. They said the fractional increase in the volume is dash. Now, how we are going to solve this question is more or less using this. But I'm going to say one or two things about fractional increase. Just take note of these values in your notes. When you hear fractional increase, it simply means by what fraction did you multiply the initial volume to get your final volume. And that is simple. Let's first find our final volume. And there are two ways to solve it. Let's first find our final volume. Our final volume is going to be V1. What's our V1? Our V1 is 30. 30 divided by our T1, which is now 323, equals our V2, which is what we're looking for, all divided by our T2, which is 353. Cross multiplying, you find out that V2 will be equals 30 times 353 divided by 323. I beg no na pass me calculator there. I beg. Okay, so what we have is 30 times 353, right? Jesus, sorry. 30 times 353 divided by 323, and that is going to give us, what did you guys get? 32.786, and that's the new volume. Now, they did not ask us to find the new volume. They asked us to find the fractional increase, and it is quite simple to get the fractional increase. When you are looking for the fractional increase, it simply means by what fraction did you multiply the initial volume to get the last volume. And how do you do that? To find the fractional increase, you simply do, okay, so let me just put down that formula. Fractional increase, let's call it Fi, is simply equals the final volume divided by the initial volume. And if you do that, what is your final volume? 32.7 divided by 30, which is the initial volume. And when you do that, calculator, our answer is going to be equals 1.090. So have that in mind, that is how to find fractional increase. Once you are looking for the fractional increase is final volume divided by initial volume. So what I was expecting is that you guys get your first volume, the final volume first, and then with the final volume, fractional increase equals final volume divided by initial volume. Okay, so I presume that was actually simple and understandable. Now, before I go to the other rules, I would like to say one or two things about the Charles law graph. Yes, the Charles law graph. Let me take out this question. Yes, I will also talk about the Boy's law graph. It was an omission. Okay, so now the Charles law graph is represented, as we know, a graph has a vertical and a horizontal axis. This is the vertical axis, while this is the horizontal axis. In the vertical axis for Charles law, you have volume. This is Charles. Yes, that's Charles. And then in the horizontal angle, you have your temperature. Now, when your temperature is in Kelvin, temperature in Kelvin starts from 0. I've always said is that the lowest possible temperature in which gases cease to exist, or where the volume of gases becomes 0, is 0 Kelvin. So that's why we are starting from here. Now, according to the law, volume is directly proportional to temperature, which means that once you have a direct proportionality, you have a straight line graph. So this is a Charles law graph. So once you are looking at a particular question and they say which one of these graphs represents Charles law, once you notice volume and temperature and they draw a straight line graph, automatically what this thing is trying to say is that this is a direct proportionality and this is your answer. Now, the second way to represent Charles law or yes, Charles' law is when the temperature is in degrees Celsius. Now, if we happen to draw this particular graph, you will notice that if here is temperature in degrees Celsius and here is volume, we'll find out that here is 0 degrees Celsius. But the temperature of gases do not start from 0 degrees Celsius. It starts from 0 Kelvin. And the equivalent value of 0 Kelvin now brought 0 degrees Celsius. Iyobubu minus 273 degrees Celsius. So that means we have to go to the other side. Remember, in every graph, there's a positive side and there's a negative side. On this negative side, the last one, 273 degrees Celsius. Now, remember we said it starts from 0 Kelvin. And if you don't see 0 Kelvin, what you're going to see is minus 273. So we're going to start from here. So that's why in your textbooks or some of your studies, you will notice this thing. What it's simply trying to say is that the lowest possible temperature is not 0 degrees Celsius, it's 0 Kelvin. And 0 Kelvin is equivalent to minus 273 degrees Celsius. So with that said, you have this, or you have, oh my god, but yes, let's manage. This is T in Kelvin. These two things are ways to represent Charles' law. Now, the name of this line, or the curve that you will get from this, is what we refer to as the isobar. Why is it the isobar? Because if you notice in Charles' law, pressure is constant. So this is also the isobar. So have that in mind. Okay, having said that about Charles' law, I did not mention anything about Boyle's law. So let's talk about Boyle's law. Now, Boyle's law, as we know, states that volume is inversely proportional to pressure. Whenever you have an inverse proportionality, what you are going to have is a curve. You're not going to have a straight line. So when I'm looking at volume and pressure, what I'm going to have is a curve. This is a hyperbole. So with this now, it's trying to show that the volume and pressure are inversely proportional. This is the representation of Boyle's law. And this line of volume to pressure is isotherm. Why is it isotherm? Because temperature is constant. So you have that. The volume to pressure is a curve. Now, before I move ahead of this, I would also like to say that the other way to represent it is this. If you look at your proportionality, we can also say volume is directly proportional to 1 over P. It's the same thing as saying volume is inversely proportional to P. And remember that I said once is direct proportionality, straight line. Once is direct proportionality, straight line. So if I want to say volume and 1 over P, I will say volume is direct proportional to 1 over P, which means our curve will now look something like V 1 over P. In this case now, when volume and 1 over P is related, we will not use hyperbole. What we are going to use is a straight line. So if you see volume to pressure, you have a curve. If you see volume to 1 over P, you have a straight line. And this is what we also refer to as isotherm, because this is a relationship between volume and pressure. So any of these two you see is also a representation of Boyle's law. Now, I saw one of the questions in JAMB, and the curve was this. The curve was something like this. They gave this, I think they gave this, and then they wrote something like PV to P or something like that. And they said, which one of these curves or these lines represents Boyle's law? Now, it's very simple. Remember that we have that P, volume is inversely proportional, V is inversely proportional to P. And if we remove this proportionality sign, it means that we'll have V is equals K over P, which means that K will be equals VP. Now, or PV, this is the same thing as PV. Now, what this simply means is that PV would be constant. PV is equals constant, and constants are represented by straight lines, which means your answer is this one that is parallel to the horizontal side. So your horizontal straight line, horizontal parallel line, is simply a representation of Boyle's law. Why? PV is constant, and when you say something is constant, it means that it's not increasing, it's not decreasing, it's just going straight. So in this case, this is your answer. So these are the different ways that might try to twist the question. So you could go ahead to do personal studies on graphs. It would also help you with respect to the study. Now, having said that, the next thing we are going to talk about is the next law, which is Amonton's law. Now, some of you might not know it as Amonton's law. Amonton. Some of you might know it as pressure law. So Amonton or pressure law. Okay, so what does Amonton or pressure law simply state? It's simply trying to say that the pressure of a given mass of gas is directly proportional to absolute temperature at constant volume. So notice something. Boyle's law, constant pressure. Sorry, temperature. Charles' law, constant pressure. Amonton's law, constant volume. And that means that we are going to have P1 over T1 is equals P2 over T2. You can have T1 over P1 is equals T2 over P2. Anyhow you write it, just make sure that this relation holds. So where are we going to use this thing? Once you look at a question and you hear constant volume. Now I noticed that JAMB I don't think I've seen any question with respect to Amonton's law in JAMB. However, it's important that you take note of it. So but we could try out a question. Let's say for instance they say the initial pressure, or find, okay, let's try this question. What is the final pressure of a gas at 25 degrees? The final pressure of a gas at 25 degrees. Final pressure of a gas. So we're looking for final pressure of a gas at 25 degrees Celsius. So the temperature associated with this pressure is going to be 25 degrees Celsius, given that the initial pressure and initial temperature of the gas. So T1, initial pressure and temperature, initial pressure and temperature of the gas are 200 atm, and the initial temperature equals 50 degrees Celsius. 50 degrees Celsius. Sorry about that. So I take the question again. What is the final pressure of a gas at 25 degrees Celsius if the initial pressure and temperature are 200 atm and 50 degrees Celsius respectively? So with these values now, you will find out that I did not mention at constant volume. Sorry, I'm just putting up these questions together right now. As I said, it's not popular. I've not seen any question on this in JAMB. However, just note it that pressure to temperature relation at constant volume, you use P1 over T1 equals P2 over T2. Now if you solve this thing now, first of all is that our temperature, this is now going to be plus 273 because it needs to be converted to Kelvin, and if you do that, you are going to have 298 Kelvin. If you add the same 273 for 50 degrees, you are going to have 323 Kelvin. And if you do that, which means that our answer is going to be P1 is 200 atm divided by T1, which is now 323. What we are going to have as our P2 is what we're looking for all over the T2. T2 is 298. Cross multiplying, you find out that P2 is equals 200 times 298 divided by 323. Okay, calculator please.
184.
What we are going to have as our pressure is 184.52. Sorry about that. 184.52 atm. And that's that basically. So my point is, Amonton's law is not so obvious and so popular in gas law questions in JAMB. However, it's important to take note of it. Where you use Amonton's law is if volume is constant, pressure to temperature if volume is constant. Now the graph for Amonton's law, as we know, pressure is directly proportional to absolute temperature, which means that we're going to have a straight line graph, and that graph is called isochord. Why is it isochord? Because volume is constant basically. So once you see this, just know that you are dealing with Amonton's law. Okay, now we extend these things to the other laws. The next law we're going to briefly talk about is general gas law. General gas law is simply a combination of Boyle's law and Charles' law. Boyle's law and Charles' law. Law. Once you combine those two things, what you're going to get is general. Please, my handwriting is terrible, I know, but please manage. Just listen well. Now, when you combine Boyle's law and Charles' law, you're going to get general gas law. So let's combine it. First of all is that Boyle's law says that volume is inversely proportional to pressure. Charles' law says that volume is directly proportional to absolute temperature. Now, if you have these two things, if we happen to do a joint variation, we know what that is. If you don't know it, please go and read up. A joint variation will give us V is directly proportional to T and inversely proportional to P. Introducing a constant to remove the proportionality. Come on, increase the mic. Introducing, sorry, we want to increase the mic a little bit so that you can hear us. Increase the mic, bro.
Maybe when Nenne's going to stop talking, be like, okay, I'm stopping talking now. Like, yeah, it was very patient fools.
Okay, I think we are back. Sorry. We had to we have to resolve some technical issues. Don't mind us. Please, for those of you that just joined the class, I hope you know you can go back. You don't have to continue with us. You can go back and start the video from afresh. Hey, what does that mean? You get what I mean? My point is you can start the video afresh and go through with the class. Whenever you get to where we are, you get. Then for those that might have questions that need to go back, probably later on we'll deal with them. You get. So, and we are resolving some issues so that the class will be going as smoothly as possible. Huh? What? Why do you change clothes? Sorry. I think I'm Somebody is asking me why I change clothes. Okay. Sorry. Let's continue the class. I had to resolve some things. I beg, one on a comment section. Ayomi and Igbo. Please, this is a class. The questions you are permitted to ask are questions with respect to the study. I know I can't respond to everybody immediately, but I'm definitely going to go back and go through it and then send your comment or response back to you. Just try as much as possible to follow what we are doing. Thank you. I did not change clothes for those that want to know. Now my technician can't resolve something. But let's continue. Now, I think I was saying something initially. I said general gas equation is simply a combination of Boyle's law and Charles' law. Boyle's law is V is inverse proportional to P. Charles' law is V is direct proportional to T. So if you combine them by joint variation, you're going to have V is proportional to T directly and inverse proportional to P. Now, if we happen to introduce or remove this proportionality sign and introduce equal to, this is now going to be V is equals K, which is the constant, T all over P. Now, making K the subject of formula, we are going to have V times P all over T. Now, you might not need to know all these things that is happening here. The most important thing you need to take note of is the equation itself. And what is the equation? V1 P1 all over T1 equals V2 P2 all over T2. Now, where you use this particular thing now, this particular relation, where it is used is if you notice that volume changed, pressure changed, temperature changed. Once everything changes, you are using general gas equation. Remember, let's take it from the top. Initially we said if it is Boyle's law, what needs to be constant is temperature. If it is Charles' law, what needs to be constant is pressure. If it is Monton's law, what needs to be constant is volume. But once everything changes, nothing is constant, you notice that what you are going to be using is general gas equation. So this is where nothing, where nothing is constant. So once everything is changing, that is when you are going to use this guy. So let's get to work. Let's try out the question on that. Let's see. Let me put up the question in the screen so everybody can see it. General gas equation. Okay. So I presume that at this point you can see the question. Now, the question says, if a gas occupies a container of volume 146 cm3. Okay, so the first thing we are noticing is the initial volume. Okay. So, yes. Back to the board. Okay, so, yes. So, back to the board. So, if a gas occupies a volume of 146 cm3, so the first volume, okay. The first volume we are noticing, which is V1, is equals 146 cm3 at 18 degrees Celsius. The temperature associated with the first volume is 18 degrees Celsius. Oh my god, that doesn't look like 18. Let's get it corrected. 18 degrees Celsius. Now remember, once it is in degrees Celsius, you are not supposed to use it. You add 273 so that you convert it to Kelvin, so that the temperature will now be what? 291 Kelvin. Okay, now then we continue with the question. And 0.978 atm, so which means the first pressure, which is the pressure associated with the first volume, is 0.9, sorry about that, 0.97 atm. Okay, so that's that about the first thing. They now said, if its volume, please ignore the 156 cm3 there. I think there's a typographical error with that question. The actual thing that should be there is, what is its volume at STP? So the actual question that is supposed to be there is, what is its volume at STP? So we are looking for the volume V2 at STP. Please, STP is standard temperature and pressure, which means the new temperature, which is V2, is equal standard temperature. And we mentioned it earlier on that standard temperature is 2. Oh, sorry. Sorry about that. Sorry about that. Okay, so the new temperature is T2 is equal standard temperature, and the value of standard temperature is 273 Kelvin. That's that. Then the new volume is what we are looking for. So the new pressure, which is P2, is going to be standard pressure, and standard pressure in ATM is 1 ATM. Now if you look at this thing now, let's look at our parameters. Initial volume is 146. Final volume is what we're looking for, so there's a change. Initial temperature is 291. Final temperature is 273, so there's a change in temperature. Initial pressure is 0.97. Final pressure is 1 ATM. Now if you notice, everything changed in this question. The volume, the temperature and pressure changed. And once volume, temperature and pressure change, what you are going to use is general gas equation. Okay, so with that said, what is going to be our general gas equation formula? That's going to be V1 P1 all over T1 equals V2 P2 all over T2. Now let's get to work. V1, what's V1? V1 in the question is 146 cm cubed multiplied by P1, which is 0.97 ATM, divided by T1. Our T1 in this question is 18 degrees, but then we changed it to Kelvin, which is 291 Kelvin, and it is equals the V2, which is what we're looking for, multiplied by 1 ATM, divided by the new temperature, which is the standard temperature, and that's 273. If we happen to make V2 the subject of formula, what we are going to get is what we're going to get is 146 times 0.97 times 273 divided by 1 times 291. So the new volume is going to be equals what? Calculator, we have equals 133, and that is option A, and you have that as your answer. So let's see the question. I'm going to the comment section to see if you have questions. Okay, comment section. The questions are not clear. Please, if the questions are not clear, increase your resolution to 480. If your resolution is in 480, it's easy for you to see. It's clear enough. Increase your resolution to 480. Go to the setting of the video and increase it to 480. You get, and the questions will be clear. I think I'm having answers, and the answers, yes. C King is correct. Ambitious is correct. Maureen Onyekachi. Any other comments? If there is none, I think we can. So if you have a question with respect to what we just did, simply indicate. Just comment or say something, ask a question, or respond.
Why don't we use 760 as our standard?
Because okay. So someone asked a question and said, why is it that we did not use 760 as our standard pressure? Why didn't we use that? And that's actually simple to resolve. The simple reason is this: if you looked at the question, the initial pressure that was given was in ATM, and once your pressure is in ATM, any other pressure that you're going to relate it with has to also be in ATM. So opening at your standard, if you are looking for standard pressure, you are going to use the standard pressure value that is also in ATM, because the pressure already in the question is in ATM, and that's how it works. If, for instance, we had something like 750 millimeter mercury, it means that the standard pressure value we are going to use is 760 millimeter mercury. I hope that has been clarified. Now, with that said, we will go to the next one. Since there is no question so far, we will go to the next one. The next law we are going to get into is Avogadro's law. Avogadro's law is actually quite simple. Let's take this question out. Yes, sorry. Avogadro's law is quite simple. And what does it say? It simply states that equal volume of gases contain the same number of moles. Yes, I take it again. It simply states that equal volume of gases contain the same number of moles. What does that mean? It means that once I have gases, no matter the gas, and they have the same volume, their number of moles will be the same thing. Take, for instance, I have a container here, and I say this container, it's my container self. is 20 cm cube, and inside this 20 cm cube I have chlorine. Now if there are 5 moles of chlorine gas in 20 cm cube, it means that if I have 20 cm cube of ammonia, 20 cm cube of ammonia will still have 5 moles of ammonia. So no matter the quantity of the gas, once you are dealing with equal volume of gases, no matter the type of gas, whether it's chlorine or hydrogen or any gas at all, once their volumes are the same thing, their number of moles are exactly the same thing. So I take it again. Avogadro's law states that equal volume of gases contain the same number of moles. I take it again. Avogadro's law states that equal volumes of gases contain the same number of moles. So once I have 50 cm, or let's look at an illustration for instance now. I have 2 containers. This is 50 cm cube. This is 12 moles of chlorine. If I now ask you 50 cm cube of something like hydrogen, how many moles will it contain? The answer is what? 12 moles. Why is it 12? Because once their volumes are equal, their moles are also going to be what? Equal. That's that. Now it means that if I say what if I say 25 cm cube? If I had said 25 cm cube, it means that what I'm going to do is to cut this one by half, and here this ever will be 6 moles of ammonia, and so on and so forth. But just have that in mind that Avogadro's law says that equal volumes of gases contain the same number of moles. Okay, so I'm going to put out a question on the screen right now for us to attempt. Let's try out this question. Yes, so attempt this question. They said at the same temperature and pressure, 50 cm cube of nitrogen gas contains the same number of molecules as dash. What's the answer? This is a very obvious answer. So put out your questions, put out your answers in the comment section. So yes, the answer I've gotten so far is C. And it's simple. Why is it C? Because once they are gases, their volumes will be the same thing at constant temperature and pressure. So that's that. The answer is C, basically. So having said that, Avogadro's law is a very simple law. Another way to describe Avogadro's law is number of moles is directly proportional to volume. Number of moles is directly proportional to volume, which means N1 over V1 is equals N2 over V2. Basically, so when you are relating number of moles to volume, I just know that they are directly proportional. Hence, N1 over V1 equals N2 over V2. Well, let's leave that anyway and go to the next one, which is ideal gas equation. Now, ideal gas equation is generally represented by the formula PV equals nRT. So let's explain what these things are. P is pressure, V is volume, N is number of moles, R is what we call gas constant, and T is equals absolute temperature. Now, the pressure can be measured in anything, volume can be measured, all these things have their different units. Like pressure can be measured in ATM, millimeter mercury, and so on and so forth. Volume can be measured in dm cube, cm cube, liter, and so on and so forth. You have your number of moles is measured in moles. How will you know its number of moles? The unit will be MOLS or just MOL. That's moles. Gas constant, however, I'll come back to that. Temperature can be measured, must be measured in Kelvin. When you are solving anything with respect to gas laws, if it is given in degrees Celsius, you should convert your temperature in degrees Celsius to Kelvin. Now, gas constant is actually a constant value, and I'm going to talk about it briefly before we solve the question. Now, your R value is dependent on the units of pressure and volume. Your R value is dependent on the units of pressure and volume. Now, let me show you something about R. If we make R the subject of formula in that question, we're going to have PV all over NT. With this thing now, we can derive our various values of R. Let me explain what I mean. For instance now, if we are looking for the value of R for 1 mole of a gas at constant pressure, at standard temperature and standard pressure. It means that our standard pressure, if it is in ATM, will be 1 ATM, and then we are dealing with volume, and then in DMQ, number of moles times time. So which means R in this case will be 1 ATM multiplied by the volume, standard volume. I did not mention this before, but molar volume of a gas is the volume of 1 mole, and molar volume is equals 22.4 sorry, let me write that somewhere clearer. Molar volume is equals 22.4. When you hear molar volume, is equals 22.4 dm³ per mole. So when they say molar volume, what is the molar volume? 22.4 dm³. We know how to convert it to cm³. If we convert to cm³, it's going to be 22,400 cm³ per mole. For those that are asking how, please you can go back and check. V in dm³ is equals V in cm³ over 1000, which means V in cm³ is equals V in dm³ times 1000. So let's come back. So if we are dealing with a molar volume here, it's going to be times 22.4 dm³ divided by n. What is our n in this question? Our n is 1 mole because we said for 1 mole, and then times standard temperature, which is 273. If you do this, R is going to be equals 0.08205, something like this. Now let's find the unit. Okay, this is mole, this is Kelvin. The unit is going to be ATM dm³. ATM dm³ because they multiplied per Kelvin per mole. So if we decide to write it, it's going to be R is equals 0.08205 ATM dm³ per Kelvin per mole. Now, where you use R as 0.08205 is if the pressure is in ATM and the volume is in dm³. Usually, the gas law constant or gas constant will be given, and once you check the value, please look at the unit before you start solving. If the unit of the gas law constant is ATM dm³, it means that your pressure must be in ATM before you use this one. If the unit is in meter cube and they gave it to you in dm³, you need to convert the dm³ to meter cube before you solve. So before you solve, check for the units. Look at the question well. Check if it coincides with that given in the question. Some of the times you will be given R equals 8.31 kilojoules per Kelvin per mole. Where this one is specifically used is in a scenario where you have your pressure given in millimeter mercury. Once your pressure is given in millimeter mercury, or sorry, not millimeter mercury, when your pressure is given in Newton per meter squared, I meant to say, once your pressure is given in Newton per meter squared and your volume is in dm³, automatically it means that you are permitted to use this one. So have that in mind, that if pressure is in Newton per meter squared and volume is in dm³, it means that the one you are going to use is 8.31 kilojoules per mole. What if your pressure is now in millimeter mercury? You can either convert the millimeter mercury to ATM and use this one. Well, to understand this thing better, let's look at the question. So the question we're going to be looking at is where is it? Okay, so let's see. So let's look at the screen. The question we are looking at is a sample of a gas exerts a pressure of 8.2 atm. Let's be writing out the parameters. Let's go to the board. Okay, so let's take everything out. Remember, all these things I gave you is just to help you understand the value of R. R is usually given, but I want to show you how to use R accurately. So they said yes. So they said a sample of gas exerts a pressure of 8.2 atm. So the pressure is equals 8.2 atm. Put it out. When confined in a 2.9 dm³ container. Now please, they did not say volume, but once you see dm³, you should know that that is volume. Are you guys what I'm saying? So which means the volume there is 2.93 dm³. Moving ahead, they now said at 20 degrees Celsius, which means the temperature. How do you know it's temperature? Degrees Celsius is 20 degrees Celsius. But I've said this thing, I'm saying it again. Do not solve gas law questions with degrees Celsius. Convert to Kelvin. How? Add 273. If you add this thing now, Yawuru 293 Kelvin. The non-Igbos listening to the class, Yawuru simply means it becomes. But let's continue. Now, they now asked us to find the number of moles of gas in the sample, which means we are looking for N. And if you look at the bracket, they gave us our R value. And what is our R value in that question? The R value is equals 0.0082. Now, I want you to concentrate on the unit. They said liter ATM, which means that for me to use this 0.082 now, I have to make sure that my volume is in liter. And I told you earlier on that dm cube and liter is the same thing. And the pressure is in ATM because they said liter, ATM, and the rest of them. So notice that your pressure has to be in ATM. In this question, the pressure is in ATM. And your volume has to be in liter or in dm cube. Now, what does this mean? It means that I don't need to do any extra conversion, that I can solve with these values directly. So let's solve. What is it going to be? PV is equals nRT. My pressure is 8.2 multiplied by the volume, which is 2.93, which is going to be equals nRT. N is what we are looking for. R is 0.082 multiplied by the temperature, which is 293. And what we are going to have from this is 8.2 times. Calculator, please. Okay, someone should please hand me a calculator. I will have my own personal calculator now. Okay, so once we do that, 8.2 multiplied by 2.93 is going to give us 24.026, which is going to be 0.082 multiplied by 293 is going to give us 24. That's n times 24.026. Now, if you notice, I'm going to take everything out so that we would see it clearly. So, making n the subject of formula, you find out that n is equals 24.026 divided by 24.026, and that is going to give us 1, which means we have 1 mole, and our answer is A. Please, I presume this is quite simple to understand, so we are going to have to move ahead. As I said, the laws I want to emphasize in this class majorly are these funny ones that used to hurt some of us. If you have questions, please, you can identify. Yes. Won't see divine. Yes, your formula is correct. You can. That's what you're supposed to use. 1A correct. So let's move ahead. So let's get into the next law for today's class. And the next law for today's class is where is this law? Sorry, don't mind me. I'm trying to get the screens together. Okay, now the next law we're going to be considering after ideal gas law is Dalton's law of partial pressure, and this is where it becomes tricky. So please pay keen attention. Dalton's law is a very simple law, and what does it simply state? It states that in a mixture of gases that are not chemically combined together, the total pressure, okay, I'll try to be slower. I take it again. Dalton's law of partial pressure states that in a mixture of gases that are not chemically combined together, the total pressure of gases in the container is equal to the sum of individual partial pressures. So for those following us online, I hope you got this. If you did not get it, please comment. So we'll start. Take it again. So taking it again, I said that Dalton's law of partial pressure simply states that in a mixture of gases that are not chemically combined together, the total pressure of gases in the container is equal to the sum of the individual partial pressures of the gases in the container. Now, what this whole thing I said simply means is that when you are asked to find P total, the total pressure of gases in a container, what you do is pressure of the first gas plus pressure of the second gas plus pressure of the third gas plus pressure of the fourth gas, and so on and so forth. The point is, just keep adding all the pressures. As you add all the pressures, you are going to get the total pressure. Imagine we have a container now. Let's look at this container. Let's say inside this container now, they say I have nitrogen, and nitrogen has a pressure of 2 atm, and I have oxygen. Oxygen has a pressure of 1 atm, and I have something like ammonia. Ammonia has a pressure of 4 atm. And then I ask, what is going to be the total pressure in this container? Please, to find the total pressure is very simple. The total pressure means add the pressure of nitrogen, which is 2 atm, to that of oxygen, which is 1 atm, to that of ammonia, which is 4 atm. And once you have this thing, your total pressure is going to be 2 plus 1 plus 4, and that is equals what? 7 atm. Very simple. The concept of Dalton's law is, once you have individual partial pressures, to get the total pressure, what you simply do is you add the individual partial pressures and you get the total pressure. Now, however, JAMB can be tricky and they will not give you direct questions. They might decide to give you questions where you need to derive or find the partial pressures. We're going to discuss that in this class. But before we get to that, whenever you see a question and you notice that a gas is collected over water, the implication of that statement is that, I take it again, if you look at the question and they say a gas is collected over water, when a gas is collected over water, there are two things involved. First of all, let's say it's chlorine gas over water. Chlorine gas over water would have a combination with water vapor, because every time you have water, you would have the vapor of water surrounding it. So just have that in mind. So when I say chlorine gas is collected over water, chlorine gas over water would be combined with water vapor. So whenever you see a question and they say a gas is collected over water, it simply means that that gas and water vapor are combined. Now, according to the law I stated, I said that total pressure means add the pressure of all the gases there. So which means if you have a question and they say the pressure of a gas collected over water is so and so, the total pressure will now be equals the pressure of that gas added to the pressure of water. Once you notice or see in a question that the gas is collected over water, whatever pressure they give you there as total pressure is equal to the pressure of the gas plus the pressure of water. Now, we don't usually represent the formula like this. If we are to rewrite it, we are going to have something like total pressure, let's call it PT, is equals pressure of dry gas added to vapor pressure. Vapor pressure is the pressure of water. So you can put this down, that the total pressure of a gas collected over water, I take it again, the total pressure of a gas collected over water is equals the pressure of the dry gas plus the vapor pressure, basically. Now, with that said, we are all mathematics students, and we should understand that once you are asked to find the pressure of the dry gas, you make it subject of formula, and it's going to be pressure of dry gas equals total pressure minus vapor pressure. So when they say find the pressure of dry gas, you do total pressure minus vapor pressure, and you have the pressure of dry gas, and that's that basically. Now, as I said before, I will say again, if you have a question and they say pressure of a gas collected in water, whatever pressure they give you there is not the actual pressure of the gas. You will need to remove the vapor pressure first before you get the actual pressure of the gas. Am I communicating with you? Good. Now let's try out a question to help us understand this. You should see the question in the next 5 seconds. Okay, no, I'm not so sure. Okay, yes, the question is on the screen now. Okay, so the question says, what is the partial pressure of hydrogen gas collected over water at standard atmospheric pressure. Let's take it in bits. Now, if you look at the question, say what is the partial pressure, which means you are looking for the pressure. When you hear partial pressure simply means the pressure of a particular gas, and in that case, you are looking for the pressure of dry hydrogen. So, which means, going to the board. So, if we are going to, let's take this out. So, looking at the screen, you will notice that because we are asked to find the pressure of hydrogen, partial pressure, when you hear partial pressure of hydrogen, it's the same thing as saying the pressure of dry hydrogen gas, which means the pressure of dry hydrogen, let me use the term DH, just manage it like that. They say we should find it because you see the question, they said what is a partial pressure, so we are looking for it, of dry hydrogen gas collected over water at a standard atmospheric pressure. Now, I told you that whenever you see the term collected over water and they give you a pressure there, if they give you a statement collected over water and the pressure is given, whatever pressure is there is the total pressure. So which means the total pressure is the pressure collected over water in this question. And what they say it is at standard atmospheric pressure. Class, atmospheric pressure has the unit of 1 atm. That is standard atmospheric pressure is 1 atm. That's standard pressure. But in our question, you will notice that the answer is in millimeter mercury. So we are not going to use 1 atm. What we are going to use in this particular question is 760 millimeter mercury. I have given the values of standard pressure initially in the class, so you can go back and rewatch it. But have this in mind: standard pressure is 1 atm. Standard pressure is 760 millimeter mercury. Standard pressure is 760 torr. Standard pressure is 1.0125 times 10 to the power 5 Newton per meter square, and so on and so forth. But if you look at the options have millimeter mercury as the unit, which means the standard pressure we are going to use here will be the standard pressure that has millimeter mercury, and that is 760. I presume that I've explained this enough. So we go back to the question. They said, what is the partial pressure? Actually, once they say partial pressure, they're looking for the pressure of the dry gas, or the pressure of the gas alone, which we said is P dry hydrogen. We are looking for it over water. I said any pressure that they mention in relation to collected over water, call it the total pressure or the pressure of the wet gas. So that's the total pressure in this case. So the total pressure is 760 millimeter mercury. Now let's continue. And 25 degrees Celsius. Now, with respect to, let's put the temperature. The temperature is 25 degrees Celsius. Okay, so they said if the saturated vapor pressure of water, please, there is a little bit of typographical error there. I will call the question correctly. They said if the saturated vapor pressure of water is 23 millimeter mercury at that temperature. So if we look out, they give us the vapor pressure at that temperature. When they say that temperature, it means that we are dealing with the same temperature, 25 degrees Celsius, and the vapor pressure of water is 23 millimeter mercury. So let's call the question together now. They said, what is the partial pressure of hydrogen gas collected over water at standard pressure? Now, when you hear collected over water, it means that the value of pressure given there will be your total pressure at 25 degrees Celsius. If the saturated vapor pressure of water is 23 millimeter mercury at that temperature. So please, we are in this question looking for the pressure of dry hydrogen gas, and we know that P total is equals pressure of dry gas, okay, plus vapor pressure. Now, what we are looking for is the pressure of dry gas. In this case, it's hydrogen gas. So what is it going to be? P total minus Vp. So what's the P total here? 760 minus the vapor pressure, 23. And what is going to be our answer? Calculator. I need an actual calculator. Please, collect phone. Give me actual calculator. So what do we have? See where we are going to write the answer. Look up. This is where our answer is. If you minus it, see your answer. Carry and come here. Hey, Jesus. Wow. So the answer is what? 700 and what? 37 millimeter mercury. Is that in the option? Yes, and that's option A. So we have that basically. So taking this out, what we did simply again is P total is equals pressure of dry gas plus vapor pressure. Once you hear collected over water. Any pressure given associated with collected over water, assume it to be the total pressure, the pressure of the wet gas. So, which means that for you to find the actual pressure of the dry gas, what you are going to do is to do total pressure or pressure of wet gas minus vapor pressure. In this case, what we had was that the total pressure was standard pressure, and we're using 760 because the options are in 760. 760 in millimeter mercury, sorry, minus vapor pressure, which is 23. And once you do that, your answer is 737 millimeter mercury, and that's that basically, option A. So, if you have questions, send out your questions to the comment section. I would be addressing them if you have any question or confusion. Okay, now we're going to try another question, but this other question we're going to be trying is a combination of general gas law and this partial pressure relation. That's this one that has to do with the wet gas. We're going to do a combination of the two of them. So let's look at the question. The question is going to come up now, so we can attempt. We're going to attempt it. If just try, I'll give you 1 minute. Everybody, try out this question in 1 minute. Try out this question in 1 minute. So, try out the question. Now, remember, I said that once you have a statement collected over water, any pressure they give you associated with collected over water is not the actual pressure. You need to remove the vapor pressure from it before you apply that pressure in a question. So this is going to be a general gas equation question. I'm just telling you guys so that you won't get so confused. Just know that you're supposed to use general gas equation. However, let me see if there's any typographical error in the question. Okay, so the question says 30 cm cube of hydrogen was collected over water at 27 degrees and 780 millimeter mercury. If the vapor pressure of water at the temperature of experiment is 10 millimeter mercury. So please, they are trying to tell you the value you need to minus to get the actual pressure of the dry gas. They said it is 10 millimeter mercury. They now said calculate the volume of the gas at 760 millimeter mercury and 7 degrees Celsius. This is something very simple to solve. So you have 1 minute to solve it. The network, technical team. Okay, while you are solving that, somebody asked a question. He said, why was, that's Ugoke Amarachi, why was 25 degrees Celsius ignored? Why it was ignored is temperature. When you are solving or looking for pressure of wet gas, you are not supposed to consider or solve anything with respect to the temperature. If you look at the formula I gave you, the formula I gave you does not have anything to do with temperature. That's why we ignored it. I get it. The temperature there is simply trying to help you understand that the pressure of the gas and the pressure of water are the same thing. Just have that in mind, that for solving for dry gas, if you are looking for the dry gas, please ignore the temperature. Just ignore it. But when you are dealing with this question I gave you now, you will notice that you will not ignore the temperature, because you are not just asked to find the pressure, the volume of the dry gas. You are asked to find the volume of the dry gas at a different temperature. And once you hear at a different temperature and pressure, it means that you are dealing with general gas law. Okay, why didn't I add 273 to 25 degrees? Because I'm not going to use it for that question. But in this one, I'm going to use this 27 degrees. Why? I am solving with general gas equation and not just finding the dry gas. When I find the dry gas volume or pressure, I will now use the pressure of the dry gas to now find the volume at 760 millimeter mercury and 7 degrees. So that's why I did not add 273 to 25 degrees. Okay, so go ahead and attempt the question. I said that you're going to apply general gas equation, so please do that. We have 1 more minute. I've not gotten an answer from anybody yet.
Can I see?
Things that you are just playing with the ring. Up again, up on the big students. Don't know what you're saying. What the big? You should have said that's what you should show yourself. That. You sound good. See, my son, you know my work. Let me tell you the thing that's showing. Thanks for saying that. That aside, he's a good boy. This is how you came and joined the class. Started participating beyond this one that came with fearless.
This is 6.
How about?
Yeah, 760. Yeah, just 7. Minus 8 to remove the water and get our. Minus 6 is what? Wait, did they use it? Minus 6 is what? Minus 6 is what? From 10.
Okay, so I presume some of you have values. Nobody. 28.7.
28.4.
28.7. I think it should be 28.4. Yeah, 28.4. See, yeah, and that's correct. Sorry, I had to go and resolve some other technical issues that had to do with the body. You know, meme da here. But let's continue. Yeah, C is the answer. For those that solved it, C is the answer. So now let's solve it generally. Now let's look at the question. Huh? The question. Sorry, my pen. Yes, thank you. So the question says 30 cm³ of hydrogen was collected over water. Now let's be writing out our values. 30 cm³ of hydrogen, 30 cm³. So let's write out our values. Where is my 30 cm³? The first volume is 30 cm³. No, please don't put that on. 30 cm³. Okay, so that's the volume, initial volume. Was collected over water. Now I told you guys that once you hear collected over water, any pressure that they give you there is the pressure of the wet gas. But what you are going to use to solve is pressure of dry gas. Which means once you see collected over water, you remove vapor pressure first before you use it. So the temperature they gave us there is 27 degrees Celsius. But we know what to do now. Whenever you are giving degrees Celsius, you add 273. And then when you add it, in this case, you are going to have 300 Kelvin. Now, for the pressure, initial pressure, the initial pressure they give us is 780 millimeter mercury. But we know that this thing is wet. How do I know? They say collected over water, which means I need to first minus the vapor pressure. Vapor pressure is always going to be given. In this case, the vapor pressure was given as 10 millimeter mercury. So in minus go there. You notice here now your new initial pressure for the dry gas also opposite 770 millimeter mercury. Now, having mentioned this, we can now move ahead to get the other values. They now say calculate the volume, which means we are looking for a new volume. If calculate the volume of the gas at 760 millimeter mercury. 760 millimeter mercury happens to be the second pressure, 760 millimeter mercury at 7 degrees Celsius. So the new temperature is 7 degrees Celsius. Now, if we look at this thing, we are going to add 273 here. And if we add it, don't mind my writing. I'm just trying to avoid it so that everybody will see it. What we're going to have here is 280 Kelvin. Now, if you look at this thing, volume changed, temperature 300, 280 changed, pressure 770, 760 changed. According to what we've studied so far, once everything changes, you are going to be dealing with general gas equation. So that's V1, V1, all over T1 equals V2 P2 all over T2. The initial volume in this question is 30 multiplied by the initial pressure, which we now found to be 770, not 780. This is how JAMB wants you to fail. So make sure you remove the vapor pressure. Any pressure that is collected over water is not the original pressure. So remove vapor pressure to get the original pressure. And then all over 27 degrees. If it's in degrees Celsius, convert it to Kelvin. Here we got 300 equals V2 multiplied by P2. What's P2? Second pressure is 760 divided by 280. Cross multiplying, the new volume is now going to be what? 300 times 280 times 30 times 770 divided by 300 times 760, and then V2 is going to be equals, multiply all through, you're going to get 28.4 cm cube. So if you got the answer, let me see you. But let's continue now. So with that said, we'll continue now. So what I did was, we applied a relationship between wet gas principle under Dalton's law with general gas equation. The final part of Dalton's law we're going to talk about is the part of Dalton's law that involves finding partial pressures with mole fraction. Let's look at this question. The question will help us understand this more. Let me put out the question. The question will be out in 5, 4, 3, 2, 1. So that's the question. Now, the question says, if 0.75 moles of cyclopropane and 0.66 moles of oxygen are mixed in a vessel with a total pressure of 0.7 atm, what is the partial pressure of oxygen in the mixture? Now, if you look at this thing, we know that partial pressure formula is, Dalton's law is, yes, sorry about that. Let's go back to the board. Must know the show. Okay, sorry, I divine. This one. Okay, sorry about that. Let's continue. Now, if you look at this question now, you are asked to find the partial pressure of oxygen. And generally speaking, the concepts in solving for partial pressure is simple. I told you that Dalton's law states that the total pressure of gas is PT. Okay. The total pressure of gas is PT is equals P1 plus P2 plus as many P's as there in this particular question. Now, the problem here is that if you are asked to find total pressure, in this case it's going to be equals pressure of cyclopropane. Cyclopropane is C3H6 plus pressure of oxygen, which is P of O2. Now, they said, what is the partial pressure of oxygen, which means partial pressure of oxygen will now be this is supposed to be P total, not P2. Sorry, this is P total. Yeah, so this is going to be P total minus partial pressure of C3H6. Now let's look at our question. Were you given the P total in the question?
Yeah.
If you notice in the question, you are given the P total, but we are not given the pressure of cyclopropane. Look well, because some of you might be confused. If you look at the question, look, we'll notice that what they gave us here is 0.75 moles, not atm, not millimeter mercury. Moles is not pressure. What does that tell you? You were not given the partial pressure of CH3. And because you are not given the partial pressure of CH3, what are you supposed to do? We can't solve with this formula. So using this formula now will not work for us. Why? What we are given was the different moles and not their partial pressures. Now, having said this, how do we solve this formula? Or how do we solve this question? Very simple. First of all is that you need to understand that partial pressure of a gas is simply equals total pressure of the gas times what we call mole fraction. You might not have come across this formula before, so please put it down. Partial pressure of a gas is equals total pressure of a gas times mole fraction. That's how to find the partial pressure of a gas. So when they say find the partial pressure of oxygen and you can't find it using the normal minus and plus, what you do is total pressure of the gas. That's the, when I say total pressure, this is like the mixture in this case multiplied by mole fraction. Now, the question is, what is mole fraction? Mole fraction is simply fraction of moles. And how do we get mole fraction? First of all, it's represented by x. It's going to be, let's say I'm looking for the mole fraction of oxygen. You know there are two gases in this question. If I'm looking for the mole fraction of oxygen, it will be number of moles of oxygen divided by the total moles there, which is number of moles of oxygen plus number of moles of cyclopropane. So have that in mind, that whenever you see mole fraction is represented by x, and it is equals the number of moles of the gas you are looking for divided by the total number of moles of gases in the whole container, and that is going to give you your mole fraction. Now, with that said, it simply means that we are going to have, so it means that our mole fraction will now be equals any of gas. So anything you are looking for, the number of moles will be on the top divided by any total, and that will bring our partial pressure of gas formula to become total pressure multiplied by any of gas all over any total. And once you do this, automatically you get your partial pressure of gas. Now, I would like to say one or two things. First of all, if you are given this kind of question and you are not given number of moles, instead you are given volume, you can actually replace this number of moles and total number of the number of moles of gases and total number of moles with volume. That is to say, instead of writing that, you can now have this as your formula. P of gas equals P total times volume of gas times total volume. You can use this if it is volume, but if it is not volume, if it is mass, you will need to convert the mass to mole. If it is volume, you don't need to convert the volume to moles. You can solve directly. We already have a video on stoichiometry which shows you how to convert these things, so you can go and look them up. But once you have a particular question and it is volume, you don't need to convert the volume to mole before you solve. Why? Avogadro's law. If you remember Avogadro's law, equal volume of gases contain the same number of moles. So you don't need to convert it. You can solve directly and you get your answer. However, if you are given mass, my brother, my sister, convert the mass to mole and then put it in this formula. Now let's solve this question since we have understood the concept. If you have questions, please send them across to the comment section. Solving this question, we are looking for the partial pressure. We are looking for the partial pressure of the gas, that is P. What gas are we looking for? Partial pressure of oxygen, so P of O2 will now be the total pressure multiplied by the number of moles of O2 divided by NT. Some of you have actually gotten the answer. Please put it out if you get it. Partial pressure of oxygen will now be, total pressure in this question is, they said mix in the vessel with total pressure of 0.7 atm. 0.7 atm. Multiplied by the number of moles of oxygen is 0.66. Let's look at the question. 0.66 divided by the sum. What is the sum? 0.66 plus 0.7. My God, that is out of the screen. So let's shift our, so 0.66 plus 0.75. Oh, I presume you understand what I'm. Let's rewrite this whole thing. Okay, so as I said, partial pressure of oxygen is equals total pressure multiplied by number of moles of oxygen divided by total number of moles, and that means that the partial pressure of oxygen is going to be equals 0.7 times 0.66 divided by 0.66 plus what's that? 0.6 plus 0.75. That's, you add the number of moles, of gases inside the container. You have 0.5 here, so you add 0.5 moles plus 0.66 moles, and once you add all of them together, you get this. Now, with that said, your P of O2 is going to be 0.7. Well, this is supposed to be 7 multiplied by what's 0.66 divided by what's the total we get? 1.41. And once you do this using your calculator, your partial pressure of oxygen is going to be 0.33 atm. Quite simple. If you have questions, please ask. Okay, so I'm going to give you guys something to attempt. So you all should attempt this question in 1 minute. Everybody give me the answer. In 1 minute, give me the answer to this question. So solve, everybody. Okay, so we are back. Let's solve this and see how it goes. Now, please, everybody, pay attention. I said something initially. I said that, oh no, this is not what. No, this is not the question. Sorry about that. This is not the question. Let's get back to the question. Yes, this should be the question. Okay, yeah, that's the question. Now, the question says, A mixture of, let's take this thing one because I notice some of you are becoming confused. I told you that these are the technical ones, so think with me. A mixture of 0.2 moles of argon. So let's write it out together. The number of moles of argon, N of argon, is 0.2 moles of argon, comma, number of moles of nitrogen, N of N2, is also 0.2 moles, and 0.3 moles of helium. So N of helium is equals 0.3 moles. Now exact a total pressure. So P total is equals 2.1 atm. The partial pressure of helium, so we are looking for P of helium, will be equals what? Now I've given you the formula straight up. Once you are given partial pressure of a gas and you notice that they did not give you the partial pressure of the other gases, that what they gave you is number of moles, you can't do P total equals P1 plus P2 plus P3. The one you are going to use is partial pressure of that gas, which is helium, is equals total pressure multiplied by N of helium all over N of helium plus N of argon plus N. Hey, okay. I think I should. Yes. Okay. Sorry about that. So yes, as I said, divided by N of helium plus N of nitrogen plus N of argon. Once you add everything, that's the total number of moles. And if you use this formula, you get your answer. Now I'm going to take everything out of the screen and then solve. So to solve it, quite simple. We are looking for the partial pressure of helium, and that is equals, total pressure in this question is 2.1 multiplied by the number of moles of helium. Because we are looking at the partial pressure of helium, the number of moles will be on top now, and that is going to be 0.3 divided by, so we now add them, 0.3. All the number of moles you are seeing there, just add it. 0.3 plus 0.3 plus 0.2 plus 0.2. If you do this, your partial pressure of helium will now be 2.1 multiplied by 0.3 divided by 0.7. You are mathematics students now. This can cancel this and give you 3. So which means the partial pressure of helium is going to be 0.9 atm, and that's that. So please, I hope this is clear. For those online that are getting 0.7, I don't know, look at what I'm doing and resolve it, and obviously you would understand it. If you still do not understand, you would call our attention. Probably we'll get to do it or review the video. You can actually go back and look at it again. Then if you have questions, you send it across. Thank you very much. Those in the physical class, clear? Okay, now moving ahead, the next law we are going to consider, that's the end of Dalton's law, is Gay-Lussac's law. We are done with Dalton's law, so let's get into Gay-Lussac's law. Now, Gay-Lussac's law, what does it state? Let me take this question away. Let me take this question out so we can move ahead. Okay, so moving ahead, I said the next principle, or the next thing we are going to discuss, is Gay-Lussac's law. What is Gay-Lussac's law? It's a very simple law. First of all, Gay-Lussac's law is the only law, or the only gas law, that is dealing with a chemical reaction. Every other law does not deal with a chemical reaction. And what does it say? It states that when gases combine, they do so in volumes that are in simple ratios to one another and to the product if gaseous. When gases combine they do so in volumes that are in simple ratios to one another and to the product if gaseous. Okay, so if you are done writing this thing, I would like to take it out. And what is it trying to say? It's just trying to say that anytime a gas is reacting with a gas, let's say for instance you have that carbon 2 oxide, which is a gas, is reacting with oxygen, which is also a gas, to give CO2, which is also a gas. Let's balance it before you do anything with Gelu's law. First balance it. If we are balancing, oxygen is not 2 is now balanced. So you find out that there is a ratio here, the ratio of the number of moles. Okay, before I continue, please, that ratio that is being talked about is equivalent to the ratio of number of moles in the balance equation. So when they say when gases react, they do so in a volume which is in a ratio. The ratio being mentioned is the ratio in the balance equation. What is the ratio we are seeing in this equation now? 2 of CO is to 1 is to 2. So any volume we are reacting has to coincide with this ratio. Now please, if you notice, and they said and to the products if it is gaseous, it means that if this product now was liquid, we are not going to include it in our ratio. If it is not gaseous, then we are not going to need to include it in our ratio. But because here is gaseous, that's why we have to include the number of moles too. Now, what does this mean? It means that when I'm reacting volumes 10 cm cube, I need to follow this ratio. If I'm reacting 10 cm cube and the ratio is 2 is to 1, if I'm reacting 10 cm cube of CO, what I'm going to get here is 5 cm cube of oxygen. It's common sense. How did I get it? If 2 is equals 10, 1 will be equals x. Cross multiplying, x will now be equals 10 over 2, which is equals 5. So have that in mind. Whenever you are dealing with a particular volume reaction or gaseous reaction, the volumes are in a simple ratio to one another. That is what Geluzat is trying to say. Now, JAMB, however, will not ask you, okay, let's look at the product too. Because the product is gaseous, it means that we can involve it too. So if you have 5 cm cube here, it means that here would also be 10 cm cube. So you have that, that's the ratio. The volumes are in the same ratio as the ratio of the number of moles. Okay, let's try out something. Imagine, for instance, you had a different reaction. Let's say you had nitrogen plus hydrogen reacting to give ammonia. Now it's balanced in this way. This is gas, gas, gas. The ratio we are seeing here is 1 is to 3 is to 2, which means if I have 10 cm cube here, what volume of hydrogen am I going to have here? 30 cm cube. How did I get it? If 1 is 10, let's solve it. If 1 is 10, that means that 3 will be what? X. Cross multiply, x is equals how many? 30. Now, what if I'm looking for 2 in this case? I can do the same thing with any one of them that I now have. I will now say if 3 is 30, that means 2 is x. How do I get it? X is equals 30 times 2 all over 3, and that is going to give me 20 because this will cancel 30. This is 10. 10 times 2. So what we have here? 20 cm cube. Now, having understood this ratio, the thing about JAMB questions is they will now try to twist it so that you would misunderstand it. But before I get to the twist, let's look up and see this. If, for instance, I tell you that I want to cook jollof rice, and I have 5 cups of jollof rice, and I need to cook it with about 3 Maggi cubes, and then I have 1 pot. Now, this is the standard way to cook jollof rice. Once you put Maggi inside 5 cups of rice, you get 1 pot of jollof rice. This is not the standard way, just an illustration. Now, however, having said this, imagine now, for instance, that I was giving, instead of giving 5 cups, I was giving 10 cups. And then, added to the 10 cups, I was giving 20 cubes of Maggi. Now, am I going to just combine the 10 cups and the 20 together like this? No. For me to combine, I'm going to consider the ratio. What is the ratio? 5 is to 3. And in this 5 is to 3, I'm going to be using the limited one to determine it. The limited one is that one that will finish after you combine the two of them. The ratio is 5 is to 3. but what I have is 10 cups and 20 Maggi. Am I going to use 10 cups to determine the number of Maggi cubes I'm going to use, or use the number of Maggi to determine the rice? You will notice that I'm supposed to use the rice because it's limited. Now when I use the rice, I will now say 5 to cook rice. I need 5 cups will require 3 Maggi. Therefore 10 cups will now require what? X. In this case, how many Maggi cubes am I going to use? It will be 10 multiplied by 3 divided by 5, and when I cancel out, what am I going to get here? 30 over 5 is 6. So which means that for 10 cups, what I'm now going to use is not 20. What I'm going to use is 6 cubes. Now you will notice that the remaining out of 20, when I minus 6 from 20, I'm going to have 14 cubes remaining. Those 14 cubes is what we refer to as residue. Unused Maggi. We refer to this one as unused. Why did I bring up this illustration? The questions you're going to be seeing are more or less related to this. Let's look at the question, for instance. Okay, but before we look at the question, if for instance I have H2 plus oxygen reacting to give water, the first thing I said you should do is to balance it. This is gas, all of them are gaseous, just know, all of them are gaseous. Now, if you have this now, the ratio is 2:1:2. Any value you are given in your question is what we call given volume. The given volume is not necessarily what you are going to use to react. Take for instance, your mommy sends you to market and say, go and buy me 1 bag of rice and 4 cubes of Maggi. You come back with the 1 bag and 4 cubes, and she now tells you, go and cook. Are you going to go and cook the whole 1 bag of rice? No. You are going to check. If she says I should go and cook, am I going to use the 1 bag to determine the Maggi cubes, or the cubes to determine the rice? You notice because the Maggi is limited, I am going to use the Maggi cube to now know how many cups of rice out of the 1 bag I'm going to cook. Why I'm saying this is, you can be given a volume. Let's say here they gave us 50 cm cube, and they gave us 50 cm cube. It doesn't mean that we are going to react 50 with 50. We are now going to consider and then check for the reacted volume. How are you going to know the reacted volume? You check. If I use 50 here, what do I need to use here? That's the question. If I use 50 here, what I'm supposed to use here originally is 25. Why? It's 2:1. You can calculate it if you want. If 2 is 50, it means that 1 will not be 50. So find what 1 will be. 1 will be x, cross multiplying, x is going to be 50 over 2, and that is going to be 25. So please, the main thing here is what is reacting. And we found out that what is reacting in this case is 25. Now, if I now ask you, you are given 50, what you reacted is 25. What gas or what amount of gas did you not use? You find out that you simply do 50 minus 25, and what you did not use is 25 cm cube of oxygen. The question can also come in the form of which of these gases is the unused gas, or the gas in excess. The gas that is in excess is oxygen because you did not use all of them. The limited gas is hydrogen because you use everything. So just have that in mind. Now whenever you are trying to do this, you check. Obona, if you have 50, if you have 2 and it gives 50, 2:50, will it give the exact correct proportion when you are dealing with it? And you use that to determine it. Now, take for instance, we have the same water reaction. Let's use water before we get to a question. And we have H2O gas. Now, in this reaction now, the ratio is still 2:1:2. Imagine in the question, the given volume was, let's say here was 100. Okay, let's use 30 here. Let's use 30, and here we have 10. Now, for us to find the reacted volume is quite simple. Now, we would say if 2 gives 30, 1 will give how many? Let's find that out. If 2 gives 30, 1 will give x. In this case, you find out that it's supposed to be 15 cm cube. So 1 up should have 15 cm cube. But if you look at it, do you have up to 15 cm cube? No. Once you don't have up to that amount, it means that that particular guy you are dealing with is the limited guy. So you are not going to use 30 to check and 2. What you are going to use is 1 and 10 to check. The reason is because 10 is the limited. It is not limited because it's smaller. It is simply limited because it will finish after the reaction. Now, if we happen to use 1 to check, when we used 2 to check, what we got was 15, and you don't have up to 15, so that means you shouldn't use 2 to check. That means you're going to use 1. So let's go and use 1. If we use 1 to check, we will say 1 is equals 10. Therefore, 2 should now be equals x. If you do this, your x is going to be 20. And if you check, do you have up to 20 cm cube? Yes. And that means that is a correct relation. So if you use 10 here, what should be here would be 20. Now, if you look at this analysis now, you find out that the one that is now excess is hydrogen gas. And when they ask you to find the volume of the unused gas, what do? 30 minus 20. And what is the volume of the unused gas? 10. So volume of unused gas is equals 10. Okay, so from all these things we've been learning, we have learned one formula. The formula we just got is that when they say find the volume of unused gas, you simply say given volume of excess gas. Excess gas is that one that will still remain after the reaction, minus given volume of oh my god, no, sorry about that, given volume of excess gas minus reacted volume of excess gas. The excess gas is the one that we'll find out that will still remain. So once you do the given volume minus the reacted volume, you're going to get the volume of the unused gas, basically. So put this down, given volume of unused gas is equals given volume of excess gas minus reacted volume of excess gas. Now, the second formula I'm going to give you is the formula of residue gas or residual gas or the remaining gas. They can say residue, they can say residual, they can say remaining gas. The residual gas formula is simply volume of unused gas plus volume of gaseous products. Please, I'm using acronyms so I can accommodate. This is volume of unused gas plus volume of gaseous product, and it will give you your residual gas. So anytime you are asked to find the residual gas, just add the unused gas, which is found by doing this, to the gaseous product. Now, if your product is not gaseous, it means that the volume is 0 now. I guess what I'm saying. So have that in mind, that once the product is not gaseous, the volume of gaseous product is 0. Now, let's look at the question to help us understand this. Okay, so the question is coming up now. Okay, sorry, let's resize it so it will fit into the screen properly. Oh, that's not the question I want to resize. Okay, so let's resize it. Okay, I think yes. So at this point you can see it clearly. Okay, now the question says 60 cm cube of hydrogen gas are packed with 20 cm cube of oxygen at 100 degrees Celsius and 1 atmosphere. Please, the term sparked with is the same thing as are reacted with. So we have that. So you have that in mind, that sparked with, reacted with, they mean the same thing. Sparked with 20 cm cube of oxygen gas at 100 degrees Celsius and 1 atmosphere. The total pressure of residual gases is dash. Hey, did I say total pressure? The total volume of residual gases is dash. Now, it's very simple to resolve. Anytime we are asked to find residual gas, the formula we have for residual gas is volume of unused gas plus volume of gaseous product. Now, we need to find this and find this before we come to residual gas. So let's find those two things first. And to find them, we need to consider the reaction. Oh yeah, the reaction says hydrogen reacts with oxygen to give water. And if you balance, you have 2 and 2. Now, from the equation, this is going to give is gaseous, and then is water vapor that is produced. Yes, when you spark hydrogen with oxygen, what you get first is water vapor. Then if it condenses, and if you notice, they said at 100 degrees, which means it is still in vapor form. Now, with that said, what you are going to have here is the ratio is 2 is to 1 is to 2. The given volume is the volume that you have in the question, and that of hydrogen is 60. The given volume of oxygen is 20, and we don't have any volume for the product. Now remember, you don't use the given volume. What you use, or you need to find first, is the reacted volume. How do we find it? Now, I do the analysis. I'll do it down here. Now, I will first use 2 and 60 to check. If 2 is equals 60, 1 should be equals x. Please, 1 is not equals 20, because this is given volume. I said don't use these things. I'm just using this to find out what should be here. If 2 is equals 60, 1 is equal x. What you are going to have is x is equals 60 over 2. If you cancel out, you have 30. Now, if you put 30 here, you will notice that you have what you were given in the question was 20, but what you are finding here is 30, which means it doesn't coincide. Are you getting? It has to be the same or less, not greater than. So that's why we cannot use this one. So we are not going to use 2 to determine. We are going to use 1 to determine. And in using 1 to determine, what it's going to look like becomes, if 1 is equals 20, therefore 2 will be equals x. Cross multiplying, you find out that x is equals 2 times 20, which is 40. Now, if you have 40 for 2, does it make sense now? Yes, because you have up to 60, and you can take 40 out of that 60. So with that said, you find out that the proper relation is if 2 is 40, that means 1 will be what? 20. So we are using 40 as the reacted volume. Now, if I ask you to find the unused gas, the unused gas will now be 60 minus 40, right? Yeah. And 60 minus 40 is 20, and that is that. If you do 20 minus 20 is 0, so which means the only gas that we do not use is 20 cm cube of hydrogen. Now, you can put this down if you want to, but I'm moving ahead. Now, haven't found that our screen is limited. So if you have with what we just said, it means that the volume of the unused gas is going to be equals, we had 60 minus 40, and that is going to be 60 minus 40 is 20 cm cube. So that's the volume of the unused gas. That's the volume of the unused gas. Now, haven't mentioned this. We are not done solving because we are looking for the residue gas. Residue gas is volume of unused gas, which is 20, plus volume of gaseous product. Now, if we checked it, I forgot to give us that, but let's look at that again. What we resolved earlier on, we said hydrogen plus oxygen is equals H2O. Sorry, that's not the reaction sign. Hydrogen plus oxygen reacts to give H2O. Balancing 2, 2. They are all gases. They are all gases, which means when I used 40 here and 20 was here, also here will be 40. So if you are asked what is the volume of the gaseous product, the volume of the gaseous product will be 40 cm cube. Is this clear? Volume of the gaseous product will be what? 40 cm cube. How did we get it? Remember that we said, let's take this back a little bit. 2 is to 1 is to 2. The given volume is 60 and 40 and 20. But after our analysis, we found out that what actually should react is 40 and 20, not 60 and 20. It doesn't go now 2 is to 1. 60 and 20 is not 2 is to 1. 60 and 20 is not 2 is to 1. And what is 2 is to 1 is 40 and 20. Now, if you have 40 and 20, it means that the product would also be 40 because it's 2 is to 1 is to 2. So which means that our residue gas will now be equals the volume of the unused gas. The volume of the unused gas we found here is 20, Abi. 60 minus 40 is 20 plus the volume of the gaseous product, which is 40. And once you add these two things, your residue gas will be 60 cm cube. And that is that. What is our answer? Our answer will be A. If you have questions, you can ask. However, as the questions are coming in, we are going to be trying out one question. Let's try out this question to help us understand this. Okay, I would simply like to say one or two things. Uh, let us let us begin to like the video. If you're understanding something, please be liking the video now. How na go take watch video where na dey learn something I no dey like? Muna like am. Muna like am. Secondly is, I think this might be the final question for today. Let's take a break from this. We'll continue some other time. We'll finish the gap for some other time. Or should we continue? If you are going to continue, you type continue. If you want us to take a break and stop for today, you type stop for today. But remember, Muna, all of now, Muna go like, sharp sharp. Okay, based on votes now, take a break is winning. I think for effectiveness, and we've been here for like close to 2 or 3 hours. We might be taking a break. You get. So after I finish solving this one, we'll continue with Graham's law in our next class, which will be rescheduled, and we'll get to know these things. So thank you very much for joining my class. What's the answer? What answer did we get for this one before we close class for today? Let's solve this one. Did I just say subscribe? This uncle impartial. Use multiplication instead of addition. I'm confused there. Nah, if you go and rewind the board, what kind of mission no kahabo? Jesus. Now, I said this before, I'm saying it again. If you can't see the question, change your video resolution. We are in the 21st century. You should know how to press phone. Change your video resolution. Now, this question is technical. Why haven't I gotten any answer? Not even one. Not even one. Yes, do I have any attempts? Somebody said 100. Somebody said 100. Aneka Rita. Is 100 even in the option? Okay, it's in the option. Okay. Let's solve to see it. Now, for you to understand the mathematics, you must understand the English. Basically, any calculation question that you don't understand the terminologies in it, or you can't interpret the English of it, I promise you, you will not understand anything. Now, let's try getting to solve this question. They said 10 cm cube of CO is mixed and sparked with 100 cm cube of air containing 21% of oxygen. Okay, so the reaction, when you put air, they said air, but what is actually going to react in that air is oxygen. So air is not oxygen. Now we know that air is made up of 78% nitrogen, 21% oxygen, and then your rare gases. So which means that what is reacting with CO inside the air is not nitrogen, it is oxygen. So let's look at it. We have CO, which is a gas, plus O2, which is a gas, and when it reacts, it's going to give us CO2. This is 2, this is 2. So everybody probably got the proportion. 2 is to 1 is to 2. Now, what I want to resolve here or get out is that the total volume of air is 100. The total volume of air is 100. But what reacted out of the air, or what is going to be used in this question out of the total air, is 21% of oxygen. Now, there are two ways to solve this thing. I think I'm going to use the easier method to explain it. Probably I'll talk about the harder method. Now let's get to work. Now you have that 2CO, the given volume of CO according to the question is 10. And then the given volume of oxygen, let's just use the total volume of air there and put 100 as the given. Now, if we are going to perform a reaction, the reaction of 2 is to 1 is definitely 10 is to 5. Are we seeing this? It's 10 is to 5, it's obvious. 2, if you have 10 here, what will react inside 100 is 5. So 10 is to 5. And once you have 10 is to 5, it means that the volume of air, which includes oxygen, that did not react is 100 minus 5. And what do we have? 95. This is unused gas. Unused gas is 95. Now, reacted volume, we use the ratio 2 is to 1 is to 2, which means 10 is to 5 is to what? 10. So we have that the volume of the gaseous product is 10. If you are now looking for residual gas, it is equals unused gas. What do we have as the unused gas? 95 plus the volume of the gaseous product, which is 10. So our answer is going to be equals 105 cm. And that's option D. C. Sorry. That's option C. And so,
21
and that's now what I'm saying is the reason I use this method is this is an easier method to understand it. You get, I did not apply the 25% intentionally in this one. This is an easier way to understand it. Now, if we decide to use or consider the 21%, how we are going to solve it is this. It's still the same way. First of all, you write down the reaction. We have CO, which is a gas, plus oxygen, which is a gas, would give CO2. That's 2CO2, which is a gas. This is 2 here. And if you do this, our ratio is 2 is to 1 is to 2. Now, on the side here, let's resolve something. You have 100 cm cube of air. But out of the 100 cm cube, what is oxygen is 21%. So, the oxygen we need for this reaction would be 21 over 100 times 100. That's how to, 21% means 21 over 100. So when you cancel out the 100, it means that the volume of oxygen inside 100 cm cube is how many? 21. I hope this is clear. So you have that the given volume of CO is 10. Given volume of oxygen is 21. Now, How do we find the reacted volume? Very simple. This is going to be used to determine. If you look at itself, you will know that you won't use 21 to determine. If you use 21, you will need 10.5. Sorry, what am I saying? If you use 21, you will need 42. It's 2:1 now. So you have 10:5 or 21:42. But you don't have up to 42 here. What you have 10. So you are using this one to determine. So with that said, it's going to be 10:5. Now, if you have 10:5, the one that did not react will now be 21 minus 5. If you do that, what do we get? That's going to be 16, right? Is it? 21 minus 5 is 16, yes. So you have 16 here as unused oxygen gas. This is unused oxygen gas, 16 cm3. Now that we have gotten this, we remember that this is 10:5 is to 10. 10:5 is to 10. Now, I want to just rewrite the parameters clearly. How did we get the unused gas now? 21 minus 5. That is for oxygen. Now, to get our values, first of all is that we found out that the volume of unused gas was now the given volume, which is 21, minus the reacted volume, which is 5. And what we have as volume of unused oxygen is 16. Now, I hope we still remember that out of that 100 cm3 of air is the gas. We minus 21, and what was remaining there was how many? 79. Now, if we have 79 of a gas, those gases are also gases, and they are not used. So because they are also considered unused gas, we are going to do both the unused of oxygen plus the unused of the other gases. If you add it together, your total volume of unused gas will now be 16 plus 79, and that is 95. Now, having gotten the total volume of unused gases, we can now say residue gas is equals, unused gas is 95 plus the volume of gaseous product, which is 10, and then you still get 105. So these are the two ways to solve it. Anyone that is easier for you, you just use. Okay.
So,
yes. How did we get 95 in the other one? Okay. How we got 95 in the other one is, let's go back. Someone was asking the question how we got 95 in the other one. We had the reaction. Reaction is 2CO plus O2 reacting to give 2CO2. Please, all of them are gases. I don't want to put the states for want of time. Now, what we are, the ratio is 2:1:2. The given volume in the question is 10 of CO and 100 of air. You get what I'm saying? So we just called oxygen air in this case. We assumed that since it's combined with air, we are combining all the volumes. Now, this is the given volume, not the reacted volume. If we are looking for the reacted volume, are we going to use 100 to determine 10 or 10 to determine 100? Obviously, 10 to determine, that's CO to determine oxygen, which is 10:5. So which means the one you did not use is given minus reacted. So we did 100 minus 5, and what you're going to get is 95. That's how we got it initially. You get. So, but any one of the ways, please, this is a video. It means we can go back. That's one advantage of this particular study. You can go back to it and cross-check what I said to understand it fully. I think we are going to be stopping here for today. In the next class, we're going to discuss Graham's law. That's the remaining law. We'll discuss it in details. If you have questions, you can put it out in the comment section or chat me up directly. I will do well to answer them. Thank you very much for watching this video. This is Wits Lounge, learning made easy. Don't forget to like, share, and subscribe. Thank you very much. Yeah.